Welcome to this free online class on machine learning. Machine learning is one of the most exciting recent technologies, and in this class, you learn about the state of the art and also gain practice implementing and deploying these algorithms yourself. You probably use a learning algorithm dozens of times a day without knowing it. Every time you use a web search engine like Google or Bing to search the internet, one of the reasons that works so well is because a learning algorithm, one implemented by Google or Microsoft, has learned how to rank web pages. Every time you use Facebook or Apple's photo tagging application and it recognizes your friends' photos, that's also machine learning. Every time you read your email and your spam filter saves you from having to wade through tons of spam email, that's also a learning algorithm. For me, one of the reasons I'm excited is the AI dream of someday building machines as intelligent as you or I. We're a long way away from that goal, but many AI researchers believe that the best way towards that goal is through learning algorithms that try to mimic how the human brain learns. I'll tell you a little about that too in this class. In this class, you learn about state-of-the-art machine learning algorithms. But it turns out just knowing the algorithms and knowing the math isn't that much good if you don't also know how to actually get this stuff to work on problems that you care about. So we've also spent a lot of time developing exercises for you to implement each of these algorithms and see how they work for yourself. So why is machine learning so prevalent today? It turns out that machine learning is a field that had grown out of the field of AI, or artificial intelligence. We wanted to build intelligent machines, and it turns out that there are a few basic things that we could program a machine to do, such as how to find the shortest path from A to B. But for the most part, we just did not know how to write AI programs to do the more interesting things, such as web search, or photo tagging, or email anti-spam. There was a realization that the only way to do these things was to have a machine learn to do it by itself. So machine learning was developed as a new capability for computers, and today it touches many segments of industry and basic science. For me, I work on machine learning, and in a typical week, I might end up talking to helicopter pilots, biologists, a bunch of computer systems people, so of my colleagues here at Stanford. And averaging 2 or 3 times a week, I'll get email from people in industry, from Silicon Valley, contacting me who have an interest in applying learning algorithms to their own problems. This is a sign of the range of problems that machine learning touches. There's autonomous robotics, computational biology, tons of things in Silicon Valley that machine learning is having an impact on. Here are some modern examples of machine learning. There's database mining. One of the reasons machine learning is so prevalent is the growth of the web and the growth of automation. All this means that we have much larger data sets than ever before. So for example, tons of Silicon Valley companies are today collecting web click data, also called clickstream data, and are trying to use machine learning algorithms to mine this data to understand the users better and to serve the users better. That's a huge segment of Silicon Valley right now. Medical records. With the advent of automation, we now have electronic medical records. So if we can turn medical records into medical knowledge, then we can start to understand disease better. Computational biology. With automation again, biologists are collecting lots of data about gene sequences, DNA sequences, and so on. And machine learning algorithms are giving us a much better understanding of the human genome and what it means to be human. And in engineering as well, in all fields of engineering, we have larger and larger data sets that we're trying to understand using learning algorithms. A second range of machine learning applications is ones that we cannot program by hand. So for example, I've worked on autonomous helicopters for many years. We just did not know how to write a computer program to make this helicopter fly by itself. The only thing that worked was to have a computer learn by itself how to fly this helicopter. Handwriting recognition. It turns out one of the reasons it's so inexpensive today to route a piece of mail across the country, so in the US and internationally, is that when you write an envelope like this, It turns out there's a learning algorithm that has learned how to read your handwriting so that it can automatically route this envelope on its way. And so it costs just a few cents to send this thing thousands of miles. And in fact, if you've seen the fields of natural language processing or computer vision, these are the fields of AI pertaining to understanding language or understanding images. Most of natural language processing, most of computer vision today is applied machine learning. Learning algorithms are also widely used for self-customizing programs. Every time you go to Amazon or Netflix or iTunes Genius and it recommends new movies or products or music to you, that's a learning algorithm. If you think about it, if you have 1 million users, there's no way to write 1 million different programs for your 1 million users. The only way to have software give these customized recommendations is if it can learn by itself to customize itself to your preferences. Finally, learning algorithms are being used today to understand human learning and to understand the brain. We'll talk about how researchers are using this to make progress towards the big AI dream. A few months ago, a student showed me an article on the top 12 IT skills, the skills that information technology hiring managers cannot say no to. It was a slightly older article, but at the top of this list of the 12 most desirable IT skills was machine learning. Here at Stanford, the number of recruiters that contact me asking if I know any graduating machine learning students is far larger than the number of machine learning students we graduate each year. So I think there's a vast unfulfilled demand for the skill set. And this is a great time to be learning about machine learning, and I hope to teach you a lot about machine learning in this course. In the next video, we'll start to give a more formal definition of what is machine learning, and we'll begin to talk about the main types of machine learning problems and algorithms. You'll pick up some of the main machine learning terminology and start to get a sense of what are the different algorithms and when each one might be appropriate. What is machine learning? In this video, we will try to define what it is and also try to give you a sense of when you want to use machine learning. Even among machine learning practitioners, there isn't a well-accepted definition of what is and what isn't machine learning. But let me show you a couple of examples of the ways that people have tried to define it. Here's the definition of what is machine learning that is due to Arthur Samuel. He defined machine learning as the field of study that gives computers the ability to learn without being explicitly programmed. Samuel's claim to fame was that back in the 1950s, he wrote a checkers playing program. And the amazing thing about this checkers playing program was that Arthur Samuel himself wasn't a very good checkers player. But what he did was he had the program play tens of thousands of games against itself. And by watching what sorts of board positions tended to lead to wins and what sort of board positions tended to lead to losses, the checkers playing program learned over time what are good board positions and what are bad board positions, and eventually learned to play checkers better than Arthur Samuel himself was able to. This was a remarkable result. Arthur Samuel himself turned out not to be a very good checkers player, but because a computer has the patience to play tens of thousands of games against itself, no human has the patience to play that many games. By doing this, the computer was able to get so much checkers playing experience that it eventually became a better checkers player than Arthur Samuel himself. This is a somewhat informal definition and an older one. Here's a slightly more recent definition by Tom Mitchell, who's a friend out in Carnegie Mellon. So Tom defines machine learning by saying that a well-posed learning problem is defined as follows. He says, a computer program is said to learn from experience E with respect to some task T and some performance measure P, if its performance on T as measured by P improves with experience E. I actually think he came up with this definition just to make it rhyme. For the checkers playing examples, the experience E would be the experience of having the program play tens of thousands of games against itself. The task T would be the task of playing checkers, and the performance measure P would be the probability that it wins the next game of checkers against some new opponent. Throughout these videos, besides me trying to teach you stuff, I'll occasionally ask you a question to make sure you understand the content. Here's one. On top is the definition of machine learning by Tom Mitchell. Let's say your email program watches which emails you do or do not flag as spam. So in an email client like this, you might click this spam button to report some email as spam, but not other emails. And based on which emails you mark as spam, say your email program learns better how to filter spam email. What is the task T in this setting? In a few seconds, the video will pause, and when it does so, you can use your mouse to select one of these 4 radio buttons to let me know which of these 4 you think is the right answer to this question. So hopefully you got that this is the right answer. Classifying emails is a task T. In fact, this definition defines a task T, a performance measure P, and this experience E. And so watching you label emails as spam or not spam, this would be the experience E. And the fraction of emails correctly classified, that might be our performance measure P. And so our task performance on the task, our system's performance on the task T on the performance measure P will improve after the experience E. In this class, I hope to teach you about various different types of learning algorithms. There are several different types of learning algorithms. The main 2 types are what we call supervised learning and unsupervised learning. I'll define what these terms mean more in the next couple videos, but it turns out that in supervised learning, the idea is we're going to teach the computer how to do something, whereas in unsupervised learning, we're going to let it learn by itself. Don't worry if these 2 terms don't make sense yet. In the next 2 videos, I'm going to say exactly what these 2 types of learning are. You might also hear other buzz terms such as reinforcement learning and recommender systems. These are other types of machine learning algorithms that we'll talk about later. But the 2 most used types of learning algorithms are probably supervised learning and unsupervised learning, and I'll define them in the next 2 videos, and we'll spend most of this class talking about these 2 types of learning algorithms. It turns out one of the other things we'll spend a lot of time on in this class is practical advice for applying learning algorithms. This is something that I feel pretty strongly about, and it's actually something that I don't know if any other university teaches. Teaching about learning algorithms is like giving a set of tools. And equally important or more important than giving you the tools is to teach you how to apply these tools. I like to make an analogy to learning to become a carpenter. Imagine that someone is teaching you how to be a carpenter and they say, here's a hammer, here's a screwdriver, here's a saw, good luck. Well, that's no good, right? You have all these tools, but the more important thing is to learn how to use these tools properly. There's a huge difference between people that know how to use these machine learning algorithms versus people that don't know how to use these tools well. Here in Silicon Valley, when I live, when I go visit different companies, even at the top Silicon Valley companies, very often I see people trying to apply machine learning algorithms to some problem, and sometimes they'll have been going at it for 6 months. But sometimes when I look at what they're doing, I say, you know, I could have told them, like, gee, I could have told you 6 months ago that you should be taking your learning algorithm and applying it in like this slightly modified way, and your chance of success would have been much higher. So what we're going to do in this class is actually spend a lot of time talking about how, if you're actually trying to develop a machine learning system, how to make those best practices type decisions about the way in which you build your system, so that when you're applying learning algorithm, you're less likely to end up one of those people who end up pursuing some path for 6 months that, you know, someone else could have figured out just wasn't going to work at all. It's just a waste of time for 6 months. So I'm actually going to spend a lot of time teaching you those sorts of best practices in machine learning and AI, and how to get this stuff to work, and how we do it, or how the best people do it in Silicon Valley and around the world. I hope to make you one of the best people at knowing how to design and build serious machine learning and AI systems. So that's machine learning, and these are the main topics I hope to teach. In the next video, I'm going to define what is supervised learning, and after that, what is unsupervised learning, and also start to talk about when you will use each of them. In this video, I'm going to define what is probably the most common type of machine learning problem, which is supervised learning. I'll define supervised learning more formally later, but it's probably best to explain or start with an example of what it is, and we'll do the formal definition later. Let's say you want to predict housing prices. A while back, a student collected data sets from the city of Portland, Oregon, and let's say you plot the data set and it looks like this. Here on the horizontal axis, the size of different houses in square feet, and on the vertical axis, the prices of different houses in thousands of dollars. So given this data, let's say you have a friend who owns a house that is, say, 750 square feet, and they're hoping to sell the house, and they want to know how much they can get for the house. So how can a learning algorithm help you? One thing a learning algorithm might be able to do is put a straight line through the data, or sort of fit a straight line to the data, and based on that, it looks like maybe their house can be sold for maybe about $150,000. But maybe this isn't the only learning algorithm you can use, and there might be a better one. For example, instead of fitting a straight line to the data, we might decide that it's better to fit a quadratic function or a second-order polynomial to this data. And if you do that and make a prediction here, then it looks like, well, maybe they can sell the house for closer to $200,000. One of the things we'll talk about later is how to choose and how to decide, do you want to fit a straight line to the data, or do you want to fit a quadratic function to the data? And there's no fair picking whichever one gives your friend the better house to sell. But each of these would be a fine example of a learning algorithm. So this is an example of a supervised learning algorithm. And the term supervised learning refers to the fact that we gave the algorithm a data set in which the, quote, right answers were given. That is, we gave it a data set of houses in which for every example in this data set, we told it what is the right price, or what is the actual price that that house sold for. And the task of the algorithm was to just produce more of these right answers, such as for this new house, that your friend may be trying to sell. To define a bit more terminology, this is also called a regression problem. And by regression problem, I mean we're trying to predict a continuous valued output, namely the price. So technically, I guess prices can be rounded off to the nearest cent. So maybe prices are actually discrete value. But usually we think of the price of a house as a row number, or as a scalar value, as a continuous value number. And the term regression refers to the fact that we're trying to predict this sort of a continuous valued attribute. Here's another supervised learning examples. Some friends and I were actually working on this earlier. Let's say you want to look at medical records and try to predict if a breast cancer is malignant or benign. If someone discovers a breast tumor, a lump in their breast, a malignant tumor is a tumor that is harmful and dangerous, and a benign tumor is a tumor that's harmless. So obviously people care a lot about this. Let's say you collect a data set, and suppose in your data set you have on your horizontal axis the size of the tumor, and on the vertical axis I'm going to plot 1 or 0, yes or no, whether or not these are examples of tumors we've seen before are malignant, which is 1, or 0, or not malignant, or benign. So let's say your data set looks like this, where we saw a tumor of this size that turned out to be benign, one of this size, one of this size, and so on. And sadly, we also saw a few malignant tumors, so one of that size, one of that size, one of that size, so on. So in this example, I have 5 examples of benign tumors shown down here, and 5 examples of malignant tumors shown with a vertical axis value of 1. And let's say you have a friend who tragically has a breast tumor, and let's say her breast tumor size is maybe somewhere around this value. The machine learning question is, can you estimate what is the probability, what is the chance that the tumor is malignant versus benign? To introduce a bit more terminology, this is an example of a classification problem. The term classification refers to the fact that here we're trying to predict a discrete valued output, 0 or 1, malignant or benign. And it turns out that in classification problems, sometimes you can have more than 2 possible values for the output. As a concrete example, maybe there are 3 types of breast cancers, and so you may try to predict a discrete value output 0, 1, 2, or 3, where 0 may mean benign tumor, so no cancer, and 1 may mean type 1 cancer, if you have 3 types of cancer, whatever type 1 means, and 2 may mean the second type of cancer, and 3 may mean the third type of cancer. But this would also be a classification problem because there's sort of a discrete value set of outputs corresponding to no cancer, or cancer type 1, or cancer type 2, or cancer type 3. In classification problems, there is another way to plot this data. Let me show you what I mean. I'm going to use a slightly different set of symbols to plot this data. So if tumor size is going to be the attribute that I'm going to use to predict malignancy or benignness, I can also draw my data like this. I'm going to use different symbols to denote my benign and malignant or my negative and positive examples. So instead of drawing crosses, I'm now going to draw O's for the benign tumors, like so. And I'm going to keep using X's to denote my malignant tumors. Okay, I hope this figure makes sense. All I did was I took my data set on top and I just mapped it down to this real line like so, and started to use different symbols, circles and crosses, to denote malignant versus benign examples. Now, in this example, we use only one feature or one attribute, namely the tumor size, in order to predict whether tumor is malignant or benign. In other machine learning problems, we may have more than one feature or more than one attribute. Here's an example. Let's say that instead of just knowing the tumor size, we know both the age of the patient and the tumor size. In that case, maybe your data set would look like this, where I may have a set of patients with those ages and that tumor size. It may look like this, and a different set of patients that look a little different, whose tumors turn out to be malignant, as denoted by the crosses. So let's say you have a friend who tragically has a tumor, and maybe their tumor size and age falls around there. So given a data set like this, what the learning algorithm may do is fit a straight line to the data to try to separate out the malignant tumors from the benign ones. And so the learning algorithm may decide to fit a straight line like that to separate out the two classes of tumors. And, with this, hopefully we can decide that your friend's tumor is more likely, so if it's over there, that hopefully the learning algorithm will say that your friend's tumor falls on this benign side and is therefore more likely to be benign than malignant. In this example, we had two features, namely the age of the patient and the size of the tumor. In other machine learning problems, we will often have more features. And my friends that work on this problem, they actually use other features like these, which is clump thickness of the breast tumor, uniformity of cell size of the tumor, uniformity of cell shape of the tumor, and so on, and other features as well. And it turns out one of the most interesting learning algorithms that we'll see in this class is a learning algorithm that can deal with not just 2 or 3 or 5 features, but an infinite number of features. On this slide, I've listed a total of 5 different features, right? 2 on the axes and 3 more up here. But it turns out that for some learning problems, what you really want is not to use like 3 or 5 features, but instead you want to use an infinite number of features, an infinite number of attributes, so that your learning algorithm has lots of attributes or features or cues with which to make those predictions. So how do you deal with an infinite number of features? I mean, so how do you even store an infinite number of things on a computer? I mean, your computer's going to run out of memory. But it turns out that when we talk about an algorithm called the support vector machine, there'll be a neat mathematical trick that will allow a computer to deal with an infinite number of features. Imagine that I didn't just write down, 2 features here and 3 features on the right, but imagine that I wrote down an infinitely long list. I just kept writing more and more and more features, like an infinitely long list of features. Turns out we'll be able to come up with an algorithm that can deal with that. So just to recap, in this class we'll talk about supervised learning, and the idea is that in supervised learning, in every example in our data set, we are told what is the, quote, correct answer that we would have quite liked the algorithm to have predicted on that example, such as the price of the house or whether a tumor is malignant or benign. We also talked about the regression problem, and by regression, that means that our goal is to predict a continuous valued output, and we talked about the classification problem, where the goal is to predict a discrete valued output. Here's a quick wrap-up question. Suppose you're running a company and you want to develop learning algorithms to address each of 2 problems. In the first problem, you have a large inventory of identical items. So imagine that you have thousands of copies of some identical item to sell, And you want to predict how many of these items you sell over the next 3 months. In the second problem, problem 2, you have lots of users and you want to write software to examine each individual of your customers' accounts, so each one of your customers' accounts, and for each account, decide whether or not the account has been hacked or compromised. So for each of these problems, should they be treated as a classification problem or as a regression problem? When the video pauses, please use your mouse to select whichever of these 4 options on the left you think is the correct answer. So hopefully you got that this is the answer. For problem 1, I would treat this as a regression problem because if I have thousands of items, well, I would probably just treat this as a real value, as a continuous value, and treat therefore the number of items I sell as a continuous value. And for the second problem, I would treat that as a classification problem because I might say set the value I want to predict to be 0 to denote the account has not been hacked, and set the value 1 to denote an account that has been hacked into. So just like breast cancers, right? 0 are benign, 1 is malignant. So I might set this to be 0 or 1 depending on whether it's been hacked, and have an algorithm try to predict each one of these 2 discrete values. And because that's a small number of discrete values, I would therefore treat it as a classification problem. So that's it for supervised learning. And in the next video, I'll talk about unsupervised learning, which is the other major category of learning algorithm. In this video, we'll talk about the second major type of machine learning problem called unsupervised learning. In the last video, we talked about supervised learning. Back then, we got data sets that looked like this, where each example was labeled either as a positive or a negative example, whether it was a benign or malignant tumor. So for each example in supervised learning, we were told explicitly what is the so-called right answer, whether it's benign or malignant. In unsupervised learning, we're given data that looks different. We're given data that looks like this, that doesn't have any labels, or that sort of all has the same label, or really no labels. So we're given a data set, and we're not told what to do with it, and we're not told what each data point is. Instead, we're just told, here is a data set. Can you find some structure in the data? Given this data set, an unsupervised learning algorithm might decide that the data lives in 2 different clusters. And so there's one cluster, and there's a different cluster. And the unsupervised learning algorithm may break this data into these 2 separate clusters. So this is called a clustering algorithm, and this turns out to be used in many places. One example where clustering is used is in Google News. And if you've not seen this before, you can actually go to this URL, news.google.com, to take a look. What Google News does is every day it goes and looks at tens of thousands or hundreds of thousands of news stories on the web, and it groups them into cohesive news stories. For example, let's look here. The URLs here link to different news stories about the BP oil well story. So let's say I click on one of these URLs. I'm going to click on one of these URLs. What I'll get to is a web page like this. Here's a Wall Street Journal article about the BP oil well spill story. So BP kills Macondo, which is the name of the spill. And if you click on a different URL from that group, then you might get a different story. Here's a CNN story about, again, the BP oil spill. And if you click on yet a third link, then you might get, a different story. Here's the UK Guardian story about the BP oil spill. So what Google News has done is looked at tens of thousands of news stories and automatically clustered them together so that news stories that are all about the same topic get to display together. It turns out that clustering algorithms and unsupervised learning algorithms are used in many other problems as well. Here's one on understanding genomics. Here's an example of DNA microarray data. The idea is you get a group of different individuals, and for each of them, you measure how much they do or do not have a certain gene. Technically, you measure how much certain genes are expressed. So these colors, red, green, gray, and so on, they show the degree to which different individuals do or do not have a specific gene. And what you can do is then run a clustering algorithm to group individuals into different categories or into different types of people. So this is unsupervised learning because we're not telling the algorithm in advance that, these are type 1 people, those are type 2 persons, those are type 3 persons, and so on. And instead, what we're saying is, here's a bunch of data. I don't know what's in this data. I don't know who's in what type. I don't even know what the different types of people are. But can you automatically find structure in the data for me? Can you automatically cluster the individuals into these types that I don't know in advance? Because we're not giving the algorithm the right answer for the examples in my data set, this is unsupervised learning. Unsupervised learning, or clustering, is used for a bunch of other applications. It's used to organize large computer clusters. I had some friends looking at large data centers, that is, large computer clusters, and trying to figure out which machines tend to work together. And if you can put those machines together, you can make your data center work more efficiently. Here's the second application, social network analysis. So given knowledge about which friends you email the most, or given your Facebook friends or your Google Plus circles, can we automatically identify which are cohesive groups of friends, or so which are groups of people that all know each other? Market segmentation. Many companies have huge databases of customer information. So can you look at this customer data set and automatically discover market segments and automatically group your customers into different market segments so that you can automatically and more efficiently sell or market to your different market segments together? Again, this is unsupervised learning because we have all this customer data, but we don't know in advance what are the market segments, and for the customers in our data set, we don't know in advance who is in market segment 1, who's in market segment 2, and so on. But we have to let the algorithm discover all this just from the data. Finally, it turns out that unsupervised learning is also used for, surprisingly, astronomical data analysis, and these clustering algorithms give surprisingly interesting or useful theories of how galaxies are formed. All these are examples of clustering, which is just one type of unsupervised learning. Let me tell you about another one. I'm going to tell you about the cocktail party problem. So you've been to cocktail parties before, right? Where you can imagine there's a party, room full of people, all sitting around, all talking at the same time. And there are all these overlapping voices because everyone's talking at the same time. And it's almost hard to hear the person in front of you. So maybe you have a cocktail party with two people talking at the same time. And a somewhat small cocktail party. And we're going to put 2 microphones in the room. So there are microphones. And because these microphones are at 2 different distances from the speakers, each microphone records a different combination of these 2 speakers' voices. Maybe speaker 1 is a little louder in microphone 1, and maybe speaker 2 is a little bit louder in microphone 2 because the 2 microphones are at different positions relative to the 2 speakers. But each microphone records an overlapping combination of both speakers' voices. So here's an actual recording of 2 speakers recorded by a researcher. Let me play for you what the first microphone sounds like.
1, 2, 3, 4, 5, 6, 7, 8, 9, 10.
All right, maybe not the most interesting cocktail party is 2 people counting from 1 to 10 in 2 languages, but there you go. What you just heard was the first microphone recording. Here's the second recording.
1, 2, 3, 4, 5, 6, 7, 8, 9, y 10.
So what you can do is take these 2 microphone recordings and give them to an unsupervised learning algorithm called the cocktail party algorithm, and tell the algorithm, find structure in this data for me. And what the algorithm will do is listen to these audio recordings and say, it sounds like the 2 audio recordings that are being added together or that are being summed together to produce these recordings that we had. Moreover, what the cocktail party algorithm will do is separate out these 2 audio sources that were being added or being summed together to form our recordings. And in fact, here's the first output of the cocktail party algorithm.
1, 2, 3, 4, 5, 6, 7, 8, 9, 10.
So it separated out the English voice in one of the recordings, and here's the second output.
1, 2, 3, 4, 5, 6, 7, 8, 9, y 10.
Not too bad, huh? To give you one more example, here's another recording of another similar situation. Here's the first microphone.
1, 2, 3, 4, 5, 6, 7, 8, 9, 10.
Okay, so the poor guy's gone home from the cocktail party and he's now sitting in a room by himself talking to his radio. Here's the second microphone recording.
1, 2, 3, 4, 5, 6, 7, 8, 9, 10.
When you give these two microphone recordings to the same algorithm, what it does is again say, you know, it sounds like there are two audio sources, and moreover, the algorithm says, here is the first of the audio sources I found.
1, 2, 3, 4, 5, 6, 7, 8, 9, 10.
So that wasn't perfect. It got the voice, but it also got a little bit of the music in there. Then here's the second output of the algorithm. Not too bad. In that second output, it managed to get rid of the voice entirely and just cleaned up the music and got rid of the counting from 1 to 10. So you might look at an unsupervised learning algorithm like this and ask, how complicated is it to implement this? Right? It seems like in order to build this application, it seems like to do this audio processing, you need to write a ton of code or maybe link into like a bunch of C++ or Java libraries to process audio. It seems like a really complicated program to do this audio, separating out audio and so on. It turns out the algorithm to do what you just heard, that can be done with one line of code, shown right here. It did take researchers a long time to come up with this line of code, so I'm not saying this was an easy problem, but it turns out that when you use the right programming environment, many learning algorithms can be really short programs. So this is also why in this class we're going to use the Octave programming environment. Octave is free open source software, and using a tool like Octave or MATLAB, many learning algorithms become just a few lines of code to implement. Later in this class, I'll also teach you a little bit about how to use Octave, and you'll be implementing some of these algorithms in Octave, or if you have MATLAB, you can use that too. Turns out that in Silicon Valley, for a lot of machine learning algorithms, what we do is first prototype our software in Octave, because software like Octave makes it incredibly fast to implement these learning algorithms. Here, each of these functions, like for example, the SVD function, that stands for singular value decomposition, but that turns out to be a linear algebra routine that is just built into Octave. If you were trying to do this in C++ or Java, this would be many, many lines of code linking in complex C++ or Java libraries. So you can implement this stuff in C++ or Java or Python, but it's just much more complicated to do so in those languages. What I've seen after having taught machine learning for about a decade now is that you learn much faster if you use Octave as your programming environment. And if you use Octave as your learning tool and as your prototyping tool, it will let you learn and prototype learning algorithms much more quickly. And in fact, what many people will do in the large Silicon Valley companies is in fact use an algorithm like Octave to first prototype the learning algorithm, and only after you've gotten it to work, then you migrate it to C++ or Java or whatever. It turns out that by doing things this way, you can often get your algorithm to work much faster than if you were starting out in C++. So I know that as an instructor, I get to say, trust me on this one, only a finite number of times. But for those of you who have never used these sort of Octave-type programming environments before, I'm going to ask you to trust me on this one and say that you will, I think your time, or your developer time, is one of the most valuable resources. And having seen lots of people do this, I think you as a machine learning researcher or machine learning developer will be much more productive if you learn this stuff and prototype this stuff in Octave than in some other language. Finally, to wrap up this video, I have one quick review question for you. We talked about unsupervised learning, which is a learning setting where you give the algorithm a ton of data and just ask it to find structure in the data for us. Of the following 4 examples, which of these 4 do you think would be an unsupervised learning algorithm as opposed to a supervised learning problem? For each of the 4 checkboxes on the left, check the ones for which you think unsupervised learning algorithm would be appropriate, and then click the button on the lower right to check your answer. So when the video pauses, please answer the question on the slide. So hopefully you remembered the span filter problem. If you have labeled data, of spam and non-spam email, we treat this as a supervised learning problem. The news story example, that's exactly the Google News example that we saw in this video. We saw how you can use a clustering algorithm to cluster news articles together. So that's unsupervised learning. The market segmentation example I talked about a little bit earlier. You can do that as an unsupervised learning problem because I'm just going to give my algorithm data and ask it to discover market segments automatically. And the final example, diabetes, well, that's actually just like our breast cancer example from the last video, only instead of, good and bad cancer tumors or benign and malignant tumors, we instead have diabetes or not. And so we will use that as we will solve that as a supervised learning problem, just like we did for the breast tumor data. So that's it for unsupervised learning. And in the next video, we'll delve more into specific learning algorithms and start to talk about just how these algorithms work and how you can go about implementing them.